Okay, hello everybody. Thanks for joining with me today. So we are going to continue our discussion in Chapter 2, but we are going to be moving on to Chapter 2, Section 3. And in that chapter and section, we're going to be talking mainly about functions and their graphs and kind of discussing how the graphs go along with functions. So here's an outline of what actual things we're going to be covering. We're going to talk about using a vertical line test for functions. We're going to find the zeros of a function. We're going to determine intervals on which functions are increasing or decreasing and determine relative maximum and minimum values of the function. And we are also going to find the average rate of change and identify even and odd functions. So I'll show you how to do each one of those. This section will be broken up into a few different videos here. So we're not going to do all those in one day. So the first thing we need to talk about is the graph of a function. So we've studied functions from an algebraic point of view. In this particular section, we're going to study functions from a graphical perspective. And the graph of a function f is simply the collection of ordered pairs x and then f of x such that x is in the domain of f. So you saw in the last section we begun to talk about this concept of domain and what numbers it is appropriate to substitute into the function. We're going to continue with that idea in looking at how those ordered pairs are graphed and breaking down what that graph really means. So, and this is something that you should already know, but x is the directed distance from the y-axis. So you can see right here, when you have an x value of an ordered pair, it's how far to the left or right that you go. And then the y value is how far up or down you go. So that's a quick refresher as to what an ordered pair represents graphically. Now, in this particular example, we want to use the graph of the function f to find these three things they're asking. The first thing that they're asking us to do is to find the domain of f. Now, if you recall, the domains are the x values that you are allowed to put into the function. Now, in this case, we don't know what the actual equation is of the function, but they gave us a visual representation of the domain and ranges in the form of a graph. And so what we want to do is we want to look and see what the domain is. Now, you might say, well, the domain, I can see the x's, it's right there, and it's right there, and it's right there, and it's right there. And you wouldn't be wrong. Negative 1, 0, 2, and 5 are definitely all in the domain of this function, but they are not the only numbers in that domain. And the reason why that they're not the only numbers is we don't just have a ordered pairs plotted, we actually have a graph. Now, something I actually just misspoke. This number 5 would actually not be in the domain, and it would not be in the domain because the dot itself is an open dot, which we'll talk about here in a second in our notation. So what you need to see is the domain is simply how far left and right the graph extends. So looking at this graph, the very farthest to the left that this graph goes is going to be negative 1. And the very farthest to the right that this graph goes is 5, but it does not touch 5. So it means it's included up to, but not including 5. Now, if you recall, if I were to graph something like that on a number line, and if I wanted to do like x is less than 5, for instance, we would have an open dot on the number 5, and then we would be shaded to the left. So this is kind of just like that, in that the graph goes up to 5, but does not include 5. So how do we notate that using what is called interval notation? So in the last video, you saw me list some domains, and I did it in a way that you were probably familiar with from Algebra 2. Now, as we move farther into higher level math, we use a different type of notation, which is called interval notation. And so I need to show you what a couple of the signs mean. So if you recall, when we had a less than or a greater than sign, that would simply be an open dot. In interval notation, that would also indicate that you would use parentheses. If you had less than or equal to or greater than or equal to, it would be a solid dot, and that would indicate the use of parentheses in interval notation. Sorry, not parentheses, brackets. So the first one uses parentheses, which means up to but not including. The second one uses brackets because you are including the number in the set. So now, again, looking at our graph, you can see that this graph starts at -1 and it includes -1 because it's a solid dot. And it goes all the way up to 5, but it does not include 5 because it's an open dot. So the way that we do this, and again, we are writing an interval from -1 to +5. When you list these intervals, you list them from least to greatest. So we're going from -1. We are including -1, so I'm going to use a bracket on -1. And we're going up to +5, but because we don't include +5, I'm going to use a parenthesis. And that would be how you would list the domain. So what that's saying is anything from -1 all the way up to but not including 5. Any of the numbers in between would also be okay for the domain of this function. And you can see that's the case because there is a solid line that's connecting those points from one side to the other. Now, the next problem asks us to find the function values f of -1 and f of 2. So what they're saying is find where x is -1 and get me the y value. So when I go right here, here is -1, and when I go to the point that's above -1 right here, this ordered pair, you can see when x is -1, the y value is +1. So that means that f of -1 is equal to +1. Now, in a similar fashion, we need to find where the x value is 2. So here's 2 right here. We need to go on a vertical line to where the graph is, and it takes us right there to that ordered pair. And you can see that in that ordered pair, when x is 2, y is -3. So the value f of 2 is equal to -3. And now the last question asks us about the range of the function. So if you recall, the domain was how far left and right the function goes. The range is going to be how far up and down the function goes. And we're going to use the same notation, this set notation, to indicate how far down and then how far up our function goes. In this case, the lowest that this function goes down to is -3. And the absolute highest that this function goes to is +3. And if you notice, both of those points are solid points. So we would include those two numbers, -3 and 3, in our interval notation. Since they're solid dots, we are going to use brackets in our interval. So the answer to this one would be you always go least to greatest. And again, I'm using brackets because the numbers -3 and 3 are using a solid dot. So there you go. That's how you do the first example. The next problem that we want to take a look at is going to be how to tell whether something's a function. Now, I kind of already talked about this in the last section, in that we have something called a vertical line test. And what the vertical line test allows us to do is it allows us to very quickly determine whether a graph is indeed a function. And if you remember from the last section, what causes a function or what causes a graph to not be a function is if we have a repeated x value. And what will happen is if you would plot two ordered pairs that have the same x value, they will line up vertically. And therefore, if you pass a vertical line through them, that vertical line intersects those 2 points at the same time, and it fails to be a function. So it says a vertical line test for functions, a set of points in a coordinate plane is the graph of y as a function of x, and if and only if no vertical line intersects the graph at more than one point. So as an example, I'm going to draw you quick two examples here. The first graph, if I had a parabola like this, that wasn't a very good graph. Let's go like this. There we go. Nowhere, if I were to pass a vertical line through this, will it intersect in more than one place at a time. Okay, but if I had the same type of graph, but this time that graph was sideways, like this, you can see that a vertical line would intersect that graph in more than one place at a time. Therefore, this would not be a function. So this one would be yes, and this one would be no, not a function. Now, finding zeros of a function, this is something that we have done a lot of already. I gave you a whole bunch of different ways to be able to break down polynomials and get them set equal to 0 and then find where they cross the x-axis. So this should already be familiar to you. But again, the zeros of a function f of x are the x values for which f of x equals 0. So meaning whatever x you put in here for the x value, if you put a number in there and the function equals 0, then the number that you put in is called a 0. Remember, graphically, that is where the function crosses the x-axis. So in this next problem, we actually have 3 problems in one, and they want us to find the zeros and state the domain of each function. Now I'm going to go ahead and state the domain of each function first, and then we will find the zeros. So let me show you how to do this. First thing I'm going to do is I'm going to draw some straight lines down to kind of block off where I'm going to put my work for each problem. Okay. So looking at the first one, this is just a regular old quadratic equation, 3x squared plus x minus 10. And so if you recall in the previous video, I did say there are 2 instances where you will have domain restrictions. Only 2 in this class, in this year. Those 2 instances are if you have a square root, which we have in the second one, or if you have a variable on the bottom of a fraction, which we have there. So you can see those 2, part B and part C, will have domain restrictions. The first one is simply just a parabola. There are not going to be any domain restrictions for this. So the way that you would write the domain is that you would use set notation, and this is going to be new to you, but we're going to say the domain would be from negative infinity to positive infinity. And notice with the infinities, negative or positive, that we use parentheses and not brackets. The reason being is infinity goes on forever, and we can not ever get to infinity. It's just an idea that the numbers continue on. Therefore, you use parentheses. Now we need to find the zeros. Well, that's easy enough. We're going to just set this thing equal to 0, and then we're going to solve it. Now, hopefully, you are really familiar with doing this type of problem. This is a problem we would have to use the ABC method. So we would do 3 times negative 10, which is negative 30. And then we're going to write our factors of 30 there. And it would be 5 and 6. Which of those is going to add up to be positive 1? It's going to be positive 6 and negative 5. So we're going to write 0 equals 3x squared plus 6x minus 5x plus x. Whoops, not plus x, excuse me. It would be minus 10. And then I'm going to go ahead and group like that. Take a 3x out, x plus 2. Take a negative 5 out, x plus 2. Regroup. And you can see now both of these are equal to 0. I'm going to set each one equal to 0 individually and then solve. So one of the zeros would be negative 2, and then the other one is going to be 5/3. So there are the 2 zeros. Remember, if I were to graph that parabola, that means it would cross the x-axis at 5/3, which is 1 2/3, and negative 2. So that was pretty straightforward. We've already done stuff like that. Now, this second one is definitely a little more involved. It's more involved for a couple of reasons. One, you've not solved nearly as many square root functions than you have quadratics like we did in part A. And part B is also more involved because this is going to involve a domain restriction. So again, 2 places in this class this year that you will have domain restrictions. The first one involves square root functions, and the second one involves what are called rational functions, which are functions that look like a fraction, which is what we have in part C, where you have a variable on the bottom. So what do we do when we have a square root function? Well, what we have to do is we take whatever is under the square root and we set a restriction on it. In order to take a square root and not get an imaginary number, whatever's under the square root has to be greater than or equal to 0. So I'm going to set 10 minus x squared greater than or equal to 0. And then I'm going to solve it. I'm going to solve it by subtracting 10 from both sides. Then I'm going to divide both sides by -1. Remember, when you divide both sides by -1, it does flip the sign over, the inequality sign. And then the last thing I'm going to do is take the square root. Now, this is really tricky, and you may have never even heard of this before. But whenever you take a square root of a number, you have to put a plus or minus in front of it. You've heard of that part. But with inequalities, that act of putting the plus or minus in front of it, when you write the negative square root, you have to flip the inequality sign over. So let me show you what I mean. I'm going to take both square roots, and what you end up with is x is less than or equal to positive negative square root of 10. And actually, I'm not even going to write it that way. I'm going to take the square root of both sides like this, and then I'm going to write x is less than or equal to the positive square root of 10, or x is greater than or equal to the negative square root of 10. So that's what I was talking about. When you take the square root of an inequality and you write the negative option of the plus or minus, the sign has to flip over again. So now what this is saying is x has to be smaller than the square root of 10, or x has to be greater than the negative square root of 10. And the really easy way to understand this is to draw a little graph of this. So here is the negative square root of 10. Remember, square root of 10 is going to be roughly 3. I don't know, let's say 3.3. We'll say about. Okay. Now the positive square root of 10 is going to be up here. So the first, if I were to draw a graph of this, it says less than or equal to, which would go this way. And then the second part, x is greater than or equal to, that's a solid dot, goes this way. So what you see is we have all of our numbers are sandwiched in between these two numbers, negative square root of 10 and positive square root of 10. So whatever you put in here for the x has to be between those two numbers. If you picked a number bigger than the square root of 10, you will end up with a negative number under the square root. So as an example, if I picked the number, let's say 5, if I put the number 5 in there and I square it, I get 25. And when I do 10 minus 25, I get negative 15. I can't take a square root of a negative 15 and get a real number. So by limiting our numbers between the negative square root of 10 and the positive square root of 10, we are ensuring that whatever this turns out to be will be positive and will be able to be square rooted. So we need a way, again, to write this in set notation or interval notation. So we're going to do that. We write the smallest number, which is negative square root of 10. We are allowed to be that number, so we're going to use a bracket, and then it goes up to the square root of 10, and that's also a bracket because it's allowed to be the square root of 10. And there's your interval. That is the domain. Remember, the domain is a list of x values that you are allowed to put into the function. Those are the numbers we're allowed to put in. So we found the domain. Now we need to find the zeros. Now the zeros are a lot easier because we're simply going to set that equation equal to 0 and solve it. So we have 0 equals the square root of 10 minus x squared. Now solving that, the first thing we have to do is square both sides. When I do that, I still have 0 equals 10 minus x squared. I'm going to move the x squared to the other side. And then I'm going to solve it, and I'm going to get x equals the positive negative square root of 10. So that right there is going to be where this function, if you graphed it, would cross the x-axis at positive square root of 10 and negative square root of 10. Okay, so now part C is the last type of function that we can have where we will have a domain restriction. And so as you saw in the last one, if you have a square root, you're probably going to have a domain restriction. In this one, because we have a variable on the bottom of a fraction, we are also going to have a domain restriction. So to find the domain for a rational function, which is what this is, which is a function that looks like a fraction, you cannot have the bottom equal to 0 because that goes against our rule in math of dividing by 0. So to find the domain, you're simply going to take t plus 5 and you're going to set it equal to 0 and solve for t. Now, what we get is t is -5. So what that means is t cannot be -5, because if you put -5 in right there, you'll get a 0 on the bottom. So what that's saying is you can put any number you want in that function except -5. So the domain, we need to say that. So how do we say that? Well, again, I'm going to draw a graph of this, a number line graph, and show you what we're going to try to represent with interval notation. What this is saying is you can pick x values from anywhere that you want on that number line except 5. And so you'll see that there are two distinct areas to this graph. There's this side and there's this side. So both of those sides need to be represented with that interval notation. So the first one we're going to represent is this side over here, and that side is from -infinity up to -5, but not including. So we're using a parentheses. Now the second side is going to be this side, and that is going to be from -5 to infinity. Now, how do we say that those two sets should be put together as one? Well, what we use is we use a symbol called a union symbol, and it's simply a capital U that you have to put in between those two intervals. And what that says is that the domain is a union of two sets of numbers from -infinity up to -5, and then from -5 to positive infinity. And again, I want to stress, I used parentheses on the -5 because -5 is not allowed to be included. Up to, but not including. Now, the next thing that we have to do is to find the 0 of this function. Well, that's easy enough. We just set the whole thing equal to 0. And the first thing we're going to do is we're going to multiply both sides by t plus 5. Now, when I do that, what you see is over here, 0 times anything is 0. So this side still stays 0. Those cancel out, and we're left with 2t minus 3. When I add 3 to both sides, I get 3 equals 2t. And then once I divide both sides by 2, I get t equals 3 over 2. And so what that means is that particular function will cross the x-axis at 3/2 or 1.5. It'll only cross once. These are just the solutions of all of these. So if you look here, here's the graph of the first one that we did, and it crosses where we said at -2 and then 5/3. Those were the zeros we found. Here is the graph of the second one. You can see again, it crosses the x-axis at -√10 and the +√10. And this last one only crosses the x-axis in one place at 3/2, which is what we said. Okay, so the next concept we need to talk about functions is how they are increasing or decreasing or constant, and how we notate that. So this is pretty simple. If you trace the graph with your finger from left to right, if your finger is going down, the graph is decreasing. If it's staying flat, it's constant. And if your finger is going up, it's increasing. And you can see there's a picture there that's describing this. An important thing to remember is you're always reading the graph from left to right. And what that increasing, constant, and decreasing are referring to is it's referring to the slope of the graph at that particular section. And so I'm going to skip that and go right to another example. So this is going to have you use the graphs to describe the increasing, decreasing, or constant behavior of each function. And so if we're looking at this first one, if I were to trace this graph with my finger, you can see starting from the left, it's increasing, flattens out for just a second maybe, but then it's still increasing. So that particular graph always continues to go up throughout the entire thing. So what we would say is it is increasing from -infinity to positive infinity, just like that, okay, because it's always going up. Now, the next one's a little trickier. This graph, if we look at the increasing, when we trace from left to right, it's increasing from here to here. Then the graph decreases, then the graph increases again like this. Okay, so there are three distinct sections, and those three distinct sections will need to be noted when we list the increasing, decreasing, and constant. So if I first list the increasing areas, you can see the first purple part was from negative infinity up to, now we are always listing the x values. And so it's going from negative infinity to -1. Notice I'm not including -1. Here's why. The best analogy I can give you is if you think of when you're on a swing. When you're swinging forward, for a split second, you're not moving forward or backwards till gravity kind of takes over and then pushes you backwards. So at that inflection point where you cease going forward and then you begin going backwards, there is a momentary point right there where the graph is going to be constant. And that point is also going to happen right here. So we are not including -1 in the increasing. You'll see what we do with that number in a second. So the increasing is from negative infinity to -1, but it is also going from -1 to positive infinity. Sorry, not -1. I didn't mean to say -1. From +1 to positive infinity. And again, notice that I'm not including that 1. It's after the 1, so I'm using a parenthesis and not a bracket. Now, where is it decreasing? Well, it's decreasing on that red highlighted part. So it's decreasing from -1 to +1. And notice with these intervals, we're always listing the x values of the intervals. Okay. Now, where's it constant? Well, it's constant at two individual places. And when it's not an interval, it's just one point. We list it with a squiggly bracket, and it's constant at -1 and +1. Just like that. Okay. Now, the last one's a little trickier yet, but it gives us a little bit more information because we have the piecewise defined function part listed right there, which I'm not sure there in my graph. It's writing. So there are three parts to this, and you can see there's three distinct parts. So this purple part is when t is less than 0. So that's the purple part. Then we'll go to the red part, and that's from 0 to 2. And then let's go to the blue part, which will be from greater than 2. Now, what you have to be careful is this, is this going to work? These intervals right here matter as how we draw our increasing and decreasing part. Okay, so let's take a look at that. The first part, t plus 1, is for t's that are less than 0. So it goes up to 0, but notice it does not include 0. There's no equal there. So when we draw the interval for this particular interval is from negative infinity. Whoops, didn't want to use a bracket, need to use a parenthesis. Always parenthesis with infinity and negative infinity. Negative infinity up to 0, but not including 0, so we're using a parenthesis. Now the next one goes from 0, including 0, to 2. So I'm going to write bracket 0, comma, 2, bracket. Because both the 0 and the 2 are included with the t because they're equal to. The last one is simply for numbers greater than 2. So we're going to start at 2 with a parenthesis, and then we're going to go to infinity. And infinity always uses a parenthesis as well. And that would be the interval. Okay, so this particular one would be increasing. This particular one would be constant. And then this last one would also, it would not be increasing. It would be decreasing. All right. Okay, now the last example. Oh, nope, I thought I had one more. I lied. All right, so I would like you to complete this, and we will go over it tomorrow in class. As always, if you have any questions, feel free to email me. Have a great day.